Good morning. Can people in the back hear me? Good? Okay, cool. How's it going? Hi. Yeah, so let's continue with caching. Just have a couple of quick announcements. So PA2 sign up will be coming out later today, and it's the same story as last time. You just go to Canvas and you sign up in the People tab, and it will be due by the end of the week. It should take, I don't know, 1 minute or something. And PA1 is due this Friday, and you have 2 free extra days to do it until Sunday. I think there's a bit of confusion. So the programming assignments have 2 free extra days, and you don't have to ask anybody to use that. But the like the problem sets don't, because I have to release the solutions on a schedule so that you have time to look at them during like before the exams and stuff. So that's why the schedule is as it is. Yeah, did people start on PA1? You're good? Any problems with that? If you haven't started, I suggest that you at least take a look, because the cluster will get pretty busy around the deadline time. So so it will be harder to get time as you get closer to the deadline. Mhm. The programming assignment 2 will come out on Friday. Yeah, like it will come out before the team sign up is finished. It will come out sometime during the day on Friday. Mhm. Yeah, it's just so like because if we start the sign up when the assignment comes out, then it'll take like a week, and then it will it'll keep dragging on. And the sign up should be very fast. Mhm. Thank you. So let's start with caching. Remember from last time, we were talking about this ideal cache model. And in the ideal cache model, there's 2 layers of memory. You have one processor, and the processor interacts with this cache. And the cache is connected to this unboundedly large memory. In the cache, there are m bytes. Cache line is b bytes, so there are m over b cache lines. And the main feature of this model is that memory moves in bundles through this hierarchy. So if you request 1 byte, actually you get b bytes surrounding it. And it's not an arbitrary b bytes starting at where you requested. It's the b bytes that it resides on in this upfront division of memory. In the ideal cache model, the cache is fully associative, which means that any line can go anywhere in the cache, and it takes order 1 time to access it. And we assume that we have some optimal omniscient replacement policy. And both of those are, of course, not realistic because we don't know the future in real life. And also, caches are not fully associative because it takes a long time to search if the cache is fully associative. But we have nice theorems showing that with resource augmentation, we can get within a constant factor of these generous assumptions. And so in the ideal cache model, there are 2 main performance measures. Oh, yes. Oh, omniscient means that it knows the future. Like in a program, you get some sequence of requests to memory. Like, for example, you iterate an array, so you're asking for those slots. Omniscient means that the replacement policy would know the total sequence of future requests. And you can there are theorems that show that that is an optimal algorithm when you have one processor, because you know every request that can come forward, and so the replacement policy can kick out can do management to minimize the number of cache misses. Question. And so, yeah, so there are 2 main performance measures. The first one is work, which is just the normal running time that we have been doing so far, also in work span analysis. And the new one is cache misses, usually Q, which is the number of cache lines that need to be transferred between cache and memory. So the main thing to notice is that Q is counting only the cache line transfers. It doesn't count what you're doing. So in the beginning of time, all the data is in memory, and you have to bring it, whatever you need, into the cache. And so if you bring 1 cache line from the memory into the cache, in this model, that costs order 1. And now you have b bytes, and you can do whatever you need to it in the cache. You could do like exponential work on it. And like sometimes in models, you have to make some unrealistic assumptions because you lose something in theory. In this model, it will cost you the same, whether or not you do order 1 work on that cache line or like exponential work on that cache line. We are only counting the total number of cache misses. And maybe that difference would be captured in the work. So just to recap from last time, we talked about different types of cache misses. in this ideal cache model, what kind of cache misses are not captured? What are replacement cache misses? So you can cause cache, you can still like, even with a fully associative cache, the cache is still a fixed size, so you can still run out of space in it. Maybe like out of the, so last time we talked about like 3Cs types of cache misses. Yes, conflict misses, yeah. So conflict misses, I think? Yeah. Yeah, conflict misses are if you have conflict misses are like if you wouldn't have made those misses in a fully associative cache, but you would have made them in like a set associative or direct map. So let's do an example. Oh, yes. Mhm. Yes. Yeah. So the question was, what is the difference, or the question was like, just to clarify, in a fully associative cache, we incur capacity and cold misses, because capacity is like when you run out of space, and cold misses are in the beginning of time, you have to bring it into the cache. And then the third type is conflict, which is things conflict in the same set, but maybe there is still space in the cache. So we're going to go back to matrix multiplication. Matrix multiplication is an important kernel in many problems. Dense linear algebra is one of these problems that people have been studying for 50 years and how to optimize them on parallel computers. It is related to a lot of other algorithms, like graph algorithms can often be expressed with matrix multiplication, as we will see in PA3. And matrix multiplication recently is popular in deep learning and machine learning workloads. You have to do a lot of dense matrix multiplication. And it's also a nice model problem in that it is well studied. We know a lot about dense matrix multiplication, and it's also good. There are a lot of good libraries out there uh, to implement matrix multiplication, and the baselines that are already out there are pretty hard to beat because they've been highly optimized. People have been spending a lot of time and resources optimizing matrix multiplication. So this is the most simple formulation of matrix multiplication. There are 3 loops, and for now, let's just assume they're square. So they're n by n matrices, and there are 3 loops, I, j, and k. We have 3 input matrices, A, B, C. And in this one, k is the fast-moving dimension, which is the inner dimension. So so each entry in C is a dot product between one row of A and one column of B. And k is the column dimension, is how the column dimension moves in B, and k is how the row dimension moves in A. So like moving horizontally in A and vertically in B. And the work is n cubed because there are 3 nested for loops and each one has length n. So that part is just the same as it was when we were doing work spend. To reason about the cache performance, we have to first know something about the memory layout of how the matrix is stored in memory, because we need to say like to access, for example, one row of the matrix, which is something that we will do repeatedly, how many cache misses will it take? And one natural order for the matrix to be laid out in is something called row major, which is you have a bunch of rows in your matrix and you just lay them end to end like that. Because memory, you can think of memory as like a 1D array. Does that make sense to people? Any questions so far? So assuming that the matrices are laid out in row major, we're going to use the ideal cache model to analyze just this basic 3-loop version. So like I said, in A, we're going to move horizontally. In B, we're going to move vertically. And C is just like you compute the whole entry of C before you move on to the next entry of C. So there are a few cases. The first case, n is the side length of the matrix. And this is, so in the ideal cache model, when you do cache analysis, ideally you would like to see factors of m and b in the terms. So like the work is an upper, just like kind of similar with the span, like the work is an upper bound on how many cache misses you can incur. You're not going to incur more cache misses than the total number of operations that you're going to do. But you want to do less cache misses, ideally, than the total number of operations. And in this matrix multiplication case, the cache misses depend on the size of the matrix. And basically the way this argument is going to go is if the matrix is too big to fit in the cache, then you have to incur many cache misses. If it is small enough to fit kind of in the cache, it will incur fewer cache misses, because part of it is already in the cache when you have to come back around. So we'll formalize that if n is greater than the number of cache lines you have, which is m over b, then we'll incur theta n cubed cache misses, because matrix B misses on every axis. So remember, matrix B is in row major. And so just in the first step of the loop, we're in this upper left here and here. And the next step of the loop, we move one to the right this way, and we move one down that way. And then so now we're here. And that was a cache miss because we brought in this cache line at first. But now when we go here, we have to bring in this cache line, which is not already there. So that's a second cache miss. So it clearly takes n cache misses to read this column. Now we have to come back around to do the next column of B. Like we're moving, the next entry C that we're going to compute is this one. So we need this entire row again, and this second column. And by the time we come back around, because we had this case where the side length is greater than the cache size, that means that by the time we come back up, this cache line will have been evicted because there is no space left. Because we only had m over b lines to begin with, and we have longer than m over b in the column. So we come back around, this cache line is gone, and we have to incur another n misses to read this. And we're going to make, this is n squared to make one pass through the entire matrix, and we're going to make n passes through the thing. So that's n cubed. Yeah, so one thing I didn't really mention is A does get spatial locality because you're going horizontally. And so like when you first read this first cache line of A, when you read the second element in A this way, you don't need to take another cache miss because it was already there, but the cache misses in B dominate in this case.
Well, we actually do the computation, the cache will hold A, B, C, the caches, but they all use the cache. So for A, we can't make sure it can be reused. Maybe it can be, the block may be replaced by C or B.
So for A, this cache line will still be here by the time you, because like they will be, because the cache is tall, you can hold B squared lines. So you need B rows, or you need B cache lines of this part to hold, to do B computation on A here. There are theta B elements in the cache line of A. And then to match that, to do the dot product, you need theta B elements of B. And so that would be theta B cache lines.
If we assume that the cache only has 3 cache lines, then we need maybe 2 cache lines. So when the computation is load A, load B, or C, the A will be replaced by the B. So
yeah.
A will need to be loaded again.
If you only have 3 cache lines, this is a bit subtle. So if you have an optimal replacement policy, the cache would not evict A because it would know that like you have to include the misses on B anyway. So you would hold A, you would hold C, hold A, and then just keep replacing what is in B. You actually have more than 3 cache lines. So actually you have at least B squared of them, or you have B squared bytes. So you can hold a rectangle of size B squared here, like B by B, and then that would be enough data in B to multiply with 1 cache line of A. Does that make sense? Mm-hmm. Yeah, good question. It's a bit subtle. Yeah, but here where the cache misses in A are a lower order term because we would divide n cubed by B. Mm-hmm. The cache, total number of bytes in the cache is at least b squared. So the total number of lines is at least b. Mhm.
When you're accessing column, are you in reality loading whole row just accessing?
So first you load this cache line up here, and then we're moving through B column-wise. So next you would load this cache line.
But that cache line is just that it's a number of
It's the whole row. So like it would, in a real machine, usually the cache is like, usually the line is 64 bytes. So the number is less than 64 bytes, so you'd move the whole 64 bytes. Or like not you as the software developer, the hardware would move 64 bytes through this hierarchy.
For here, it's simple since here we have only three variable kind of stuff. But if more complex computation, do we need to consider all of this? If we have a 5 matrix or 10 matrix to the computation, do we need to consider for the cache analysis, do we combine them all in the analysis of the cache?
Depends on what is the working set at one time. If you work on all 5 of them at the same time, then you need to consider them all. If it's like 2 and then like, for example, one, like let's say you wanted to sum up 10 matrices together, like first you would do the first 2 and then you would add in like the next one and the next one like that. So at any point you would only need to consider 2 at a time, or 3, I guess, 2 input, 1 output. But yeah, it depends on what is the working set currently. LRU is least recently used. So that's like a replacement policy, which is last time we talked about how if you assume LRU, you can get within a constant factor of the cache misses using resource augmentation compared to an optimal cache. So both A and B are laid out in row major. And for A, we're moving along the rows horizontally. So like A is laid, both of them are laid out in 1D. So for A, you would just make one single left to right pass, multiple left to right passes. And then for B, you would be kind of like skipping through the 1D representation because you're doing it column-wise. Yeah, so here it's not super necessary to assume a tall cache, but later on we will need it. Tall cache is you have at least B squared bytes in the cache. So that means you have at least B lines. And the reason is later when we're going to do submatrices. So right now we're doing the entire matrix multiplication at once. To improve the caching behavior, the main trick is to multiply smaller matrices at one time. And so there we need a tall cache because you need to fit like a B by B submatrix, at least B by B. Oh, C is just some constant, at least 1. Oh, the point is just so that this side length is longer than the number of lines you have. Because you have at least, you have M over B cache length. So that is the first case, which is that the matrix is just too big, that by the time you come down here, by the time you come down here, whatever is up here can't fit anymore, and so it's gone. It needs to come back around and incur this cache miss up here again. In case 2, this is like a kind of middle case, which is the side length is between square root of m and at most some constant c m over b. And so we're just going to focus again on matrix B because A actually achieves good spatial locality because it's moving left to right. And in this case, Q of n is n cubed. So now there's a factor of B in the bottom. And the reason for that is because this side length is, so the entire matrix is still too big to fit in the cache. That's why it's this case, because the matrix is actually size n squared. And so if you do n squared, this would be like greater than m, which is the number of bytes you have. So the reason for this case is like this whole matrix is too big to fit in the cache, but one column of cache lines can fit. Or one column of the matrix times b can fit. Like n times b can fit in this thing. And so by the time you come back up here, this cache line is still here. And that's why there's a factor of b in the bottom now, because you don't have to incur another miss to read this when you move to the second column. And it was always like n cubed over b for a, because it's moving through this 1D array. And finally, the last case is n, which is the side length, is less than root m. So that means n squared is less than something like root m. And so the entire thing can fit in the cache, because you have, sorry, n squared is less than m. So the entire thing can fit. And the cache misses is n squared over b, because the size of the matrix is n squared, and you at least have to read the matrix. It's going to take you a minimum of n squared over b cache misses. That's just how much it costs you to read one entire pass through the thing. It's n squared over b, and then once it's in the cache, because this matrix is small enough that the whole thing will fit, then everything is there, and you can do the entire multiplication without any further cache misses. Yes, yeah. You have to always, so in the beginning of time, everything is in the memory. And so n squared over b is the number of compulsory misses, like the number of misses that you need to incur to bring the matrix into the cache. Because the matrix size is n squared, and it has, you just read like block by block. And the reason that it was greater, like previously we had something like n cubed, is because the work is proportional to n cubed. But if you remember in the ideal cache model, with Q, we're only counting cache misses. So like the work to actually do the matrix multiplication is not counted here because it already fits in the cache. Kind of like I was saying earlier, some models always need to be a little unrealistic. So in this model, once something is in the cache, no matter how much you're doing on it, it doesn't count. It doesn't cost you anything more. We're only counting the number of cache line transfers. For A, here we're assuming that they're all n by n, so A would also be n squared over b. One thing we can do to improve the cache locality, this is like a classic trick, which is previously the loop order was ijk, and k was the fast moving dimension, and we were incurring a lot of cache misses in B because we were accessing B column-wise. But we can notice that you can do these loops in any order. You could even swap I in the middle if you want. But if you swap K and J, then C is moving this way now. J is now the slow moving dimension. So A is now like the slowest moving matrix in some sense. And both C and B are moving horizontally. So no matter how big n is, you always get at least this factor of b in the bottom because you're moving horizontally through the memory. Yeah, so next we're going to do tiling, which is a classic trick in matrix multiplication to improve the cache behavior. And basically what tiling is you cut up the matrix into submatrix multiplications. So rather than doing one full row and one full column at a time, you do a small block of, you cut A, B, and C into blocks. And these blocks for square matrices are size S by S. And the way that we would actually program this is that rather than having 3 loops, we would have 6, like a smaller one and an outer one for every dimension. Yeah, so this is, now the outer one is previously it was going up by 1, now it's going up by S at each time. and the inner one is going up by 1, but it goes like between starting point and s after the starting point. And then the most inner part is the same. This is just the dot product part. And the reasoning for this is, so it doesn't actually change the additions and multiplications that we're doing. In the end, we still need to do n cubed of those. But the reason that we're doing this is, if you think about how we're traversing through this, first we would go through this horizontal part this way. And then before we were going like through this entire row, like all the way left to right. But now when we get here, then we move on to the second row, left to right, and then the third row, left to right, like that. And it doesn't affect the work. So there are n over s quantity cubed subproblems. Each of them has work s cubed. And so that's going to get us, again, n cubed, which is unchanged, which is natural because we didn't do any fancy tricks to get subcubic matrix multiplication. But the whole reason to do this is because of cache behavior. And kind of at a high level, the goal is, if you choose S correctly, you want one of these tiles, this S by S thing is called a tile. You want, actually you want 3 of the tiles to fit in the cache. One of A, one of B, and one of C. And then you can do a whole submatrix multiplication of that tile of A and that tile of B without doing additional cache misses. And also, all the outputs that you would need are in your tile of C. So the goal is that you can, so you're not going to complete the whole, like, dot product of the entire element, but you're going to complete part of it. You're going to kind of complete like part of an entire tile. And the goal is, okay, so if we can choose S such that the submatrices just fit in the cache, which means that S is something like theta root m, so then S squared would be something like theta m. Then going back to this caching lemma that we had from last time, the caching lemma just tells us that if we know that all these segments, which are in the submatrix, can fit in the cache, it will take us s squared over b cache misses to read them. And so we're going to analyze how many cache misses we have to do. The number of subproblems is still the same, quantity n over s cubed. The cache misses per subproblem is s squared over b from this caching lemma. And you multiply them, and that is n cubed over b square root m. So previously, by loop ordering, we could only get a factor of b in the bottom. But now we have polynomial factors in m. And there's a nice paper from 81 that shows that this actually is an optimal lower bound for the problem. But something that I didn't really mention is, like, how do you choose S? So it is important that we chose S correctly for this, because if you choose it wrong, like say you choose S equal to like M, this is not going to help you to do these blocks. We just achieve the same thing that we did before. Yeah, so S is square root M. So we just plug, so like there would be an S in the bottom now, because this is like S cubed in the bottom, this is S squared in the top. So you have S in the bottom, and S is root M, or S is theta root M. Good? Yeah, good question. Yeah, so the entire thing hinges on choosing S, like theta root M. But how can we choose? Yeah, go ahead. Mhm. Oh, yeah, good question. So if we just look at this outer 3 loops, that's n over s cubed iterations. Oh, yeah, sorry. Yeah, really good point. So we look at the outer 3 ones, and that is n over s quantity cubed there. And if you look at the inner 3 ones, that's s cubed in the work. Yeah. So that's where this s cubed in the work came from, because it's like SSS. And then now we're analyzing the cache misses of these inner 3 loops. But the outer 3 ones stay the same. Good question. Thank you. Other questions? Yeah. So how do you choose this S correctly. If you know M, it's possible. And if you only need to choose one S, like if your matrices are square and you're doing one level of tiling, it may be possible to choose S correctly. However, there become issues because first, well, there are many issues. One is that in reality, you don't have two levels of cache. You actually have at least three, probably, or more. And so you have to do multi-dimensional tiling beyond two levels. And so like if you had multiple levels, then you would have two tuning parameters, now S and T. But the problem is that you can't do multi-dimensional tiling with binary, or multi-dimensional tuning using binary search. It's like if you choose S one direction, like T might need to move in another direction. And then the code also becomes complicated because now you like the more tiling you do, the more nested loops you need to do. You could do this with code generation, but manually is a bit tedious. Another issue is, yeah, so like the issue becomes even larger when you have multiple levels, even higher levels of cache. And an additional issue is like, so far we didn't really talk about the intersection of parallelism and caching, but also in reality you have multiple programs running at one time in your machine and you only have, like you have a shared cache. And so multiple things are trying to use it. And so even if you know the cache parameters, like you're given when you buy a machine, like, oh, the L1 is, I don't know, 32 kilobytes and the L2 is, I don't know, like 128 or something like that. But you have multiple programs running at a time. And so you don't know like your effective cache size at any time because there may be multiple things going on and they all need to use the shared resource. So that's another problem, and it makes it easy to mistune the parameters because let's say you chose S depending on like the cache size that they gave you when you buy the machine. That's not actually the cache size that you may experience in that particular program. So we're going to go back to divide and conquer, which can resolve some of these problems. So this is the same divide and conquer algorithm that we had before. We divide each CAB into quadrants. Just 1, 1, 1, 2, 2, 1, 2, 2, like that. And you can express the matrix multiplication as 8 recursive submatrix multiplications. So A11, B11, like this way is moving horizontally, this way is moving vertically. And this is how you would do, like, let's say these were just 4 by 4 matrices. This is just the terms that go into the dot product. So this is 8 submatrix. This is 8 recursive submatrix multiplications, and then you have to add them together. This is the recursive code, similar to what we had last time, but it's simpler in this case because now we're not worrying about parallelism. Like previously we had this complicated thing where like if you have 8 parallel calls, then you need a temporary, but this is just one thread, so we don't have to worry about the temporary. So we have matrices C, A, B, N, which is the length, and row size. Oh, N is the total length, I guess, and then row size. No, sorry, row size is the total length, and then N is like what is in the submatrix at this point, because N gets halved, and then row size stays fixed throughout the recursive calls. And this is kind of what we were doing a couple lectures ago, which is like you have to find the starting point of each submatrix, and then we have 8 recursive calls. Mm-hmm. Yeah, good point. So coarsening the base case, for simplicity, this is just at n equals 1, but if you were actually to program coarsening the base case, you would set some threshold. Like you could define threshold as like a higher level macro, and then you would say if n is at least threshold, you call into like the 3-loop version. So for just some constant, you would just use this like a 3-loop base case. And this is just how you find these upper left starting points in the submatrices. So the work is still n cubed, which is good. we didn't totally screw something up. There are 8 recursive calls. Each one has side length n/2, and there's theta1 work in each recursive call just to cut the matrix into 4. And from the master theorem, we know that this is n cubed. And okay, yeah, so this is the recursion. We start with w of n up there. There are 8 calls. Each one has size n/2. And then we cut it again. We have 8, and each one has n/4. And all the way down like that. So we can directly apply the master theorem, but the reason that I want to go through this recursion tree is that we're going to use a similar logical recursion tree to analyze the cache complexity. Yeah, so the way that we argued about the work is that the number of leaves, we first reasoned about the number of leaves, which is that we have 8-way branching. The height of the tree is log n, so that's n to the power log base 8, which is n cubed. Went all the way down. Each one has theta1 work. It's just like a single multiply add, and that's the same loop as the same as the 3 nested loops. So now we want to analyze the cache misses, and we can express using this recursion. So it's a bit more complicated because previously, when we were analyzing the work, the base case was just theta1 for n equals to 1, logically. For q of n, we still have the same recursive call, like the same high-level recursive call, which is there are 8 subproblems, and each one gets cut in half. That's theta1 work to do the cutting. But now the base case is different. The base case is, it's like the third case that we were talking about. Yeah, it's the third case that we were analyzing before, which is when all the matrices can fit into the cache. And that is theta n squared over b, if n squared, which is the matrix size, is less than some constant c of m. So this case is just saying, at some point in the recursion, all the matrices will become small enough to start fitting in the cache. And at that point, we will incur no further cache misses to do the submatrix multiplications. This is not where the recursion ends. This is just where the analysis ends. So like we will keep, from the work, we keep cutting the problem until the base case is size theta1. But from a cache miss perspective, we don't need to incur further cache misses to do those smaller submatrices. So this part is kind of subtle, but it is important, which is that like the algorithm and the analysis are somewhat separate because we are only counting the cache misses, and in this case, we only need to count if the matrix doesn't fit. So we're going to draw this recursion tree again, now using this that we have, this recurrence that we have. So the top part is the same. We have 8-way branching, and now this is q of n over 2. We cut again, so that's q of n over 4. And this part is different from the work analysis. So previously, we had log n. The height of this entire thing was log n. And the height of the actual recursion in the algorithm is still log n. But from an analysis perspective, this analysis tree is shorter because the case that we're considering in the base case is when this n squared is something like theta m. And so that is higher than the actual recursion base case, which is n is equal to 1. And so the number of leaves is less. Or sorry, the height is less because the height stops when n is like square root m. So that's where this is coming from. And the total height of the recursion is log n. From an analysis perspective, we cut off the recursion at n is theta square root m, and that's where you get the subtraction. Log n minus log square root m, and then the 1/2 goes in the front. Log rules. The number of leaves is still 8 raised to the height, but now the height is truncated due to the cache size. And the number of leaves, if you expand this out, becomes n cubed divided by m to this 3/2 power. And so the argument is similar to when we were analyzing the work. Like in the work, we were saying this is the number of leaves and this is the work per leaf. And there it was more straightforward. There are n cubed leaves and we have to do theta 1 work per leaf. Here, there are this many leaves, and how many cache misses are we going to do at each leaf? We got it from the base case in the recursion. N squared over b, and n squared is bounded by this, so this thing is theta m over b. So the way that this goes is like this. First, you figure out the recurrence, then you figure out the height, and using the branching factor and the height, you get the number of leaves. And then, so you have the number of leaves, and you have the cache misses per leaf, which is m over b, and you multiply them. So for the total cache misses, we have number of leaves times misses per leaf. That is this thing times m over b. And we get this bound, which is asymptotically the same as with tiling. So this is kind of cute actually, because notice that we didn't, this is just divide and conquer. Like we didn't use the cache parameters in the actual algorithm. But, so this is like subtle, like you don't have, to do cache analysis, the thing doesn't necessarily have to use the cache parameters. Like we kind of saw that in the beginning when we were just analyzing the base 3-loop matrix multiplication. We still see factors of b, even though like we didn't include b in the code in any way. So similarly here, we still see cache factors, even though like neither b nor m is actually in the code at any point. Questions? Okay. So this is, oh yeah, go ahead. Hmm? Yeah, so after this point, the actual algorithm can continue to split. But those submatrices are, so we bring like the larger submatrix into the cache, and then the problems may continue to split, but you incur no further cache misses to bring those smaller subproblems into the cache because those are already there. And so, yeah, so this, there's some decoupling between the algorithm, like the recursion in the algorithm and the recurrence and the analysis. Like logically, the analysis has like a truncated tree because you stop counting after the thing fits in the cache. Yeah, good question. Yeah, this part is actually quite subtle, but it is nice because divide and conquer is like, you know, it's kind of like a common paradigm, and we didn't have to think anything really about the cache parameters in the actual implementation of the algorithm, but from a theoretical perspective, you can reach this lower bound. Yeah. So just to wrap up this part, this is maybe like the most classical one of this class of algorithms, which is called cache-oblivious algorithms, which are algorithms that ideally efficiently use the cache without any tuning parameters. So like this is in contrast to tiling, which you had to give it the S, which is like the side lane of your tile. For cache obliviousness, there are no tuning parameters, like it was just divide and conquer. And there's no explicit knowledge of cache sizes in the algorithm. So we still do analysis in terms of M and B without using M and B in the code. And there is some theory to show that this can handle multi-level caches automatically. So like because in some sense, divide and conquer is like, in some sense like infinity tiling, like you just keep cutting down. So it can theoretically tile to multiple levels of cache. And there's some papers that show that it's good in multi-programming environments when you have multiple jobs running at a time. Yeah, so cache-oblivious algorithms are really nice actually. There's a whole bunch of papers about them. Matrix multiplication is one of the first ones, but there are many problems for which we know efficient cache-oblivious algorithms. Which I guess we will get to now. Oh, am I out of time? When does it end? No, I still have another like 20 minutes. All right, let's do this. Questions? Okay. So don't need to recap cache-oblivious algorithms because we were just there. But we're just going to do another problem, just to see another example of how this can work. And we're going to do this heat diffusion problem. So heat diffusion is a common thing that people do in scientific computing, which is that they run simulations on some kind of grid or some kind of spatial thing. And basically how it works is that like you start with one point or maybe a small region that has high heat, and you want to compute in the entire spatial region, how does the heat transfer over time. And when you actually write it in the code, or like, so you have some function, and you have t, x, and y for 2D. So we have x and y spatial coordinates, we have some time dimension, and we want to compute the temperature of that point over time. And in math, the way that we do that is through derivatives. We're not going to have to think too much about derivatives, but this is how they do it in math, and somehow we want to translate it into code because we want to compute this thing. So for simplicity, we're going to do it in 1D first. And in 1D, like let's say that your hot point was in the left, then it will diffuse this way, and like the further points will be colder. And here we only have one spatial dimension. So U is the heat, this thing. T is time, and X is the spatial dimension, and alpha is some constant. Don't worry too much about this. We don't really do calculus here. But we're gonna do, this is basic calculus, which is like the way you take, this is like, like for the street-form calculus, you take the derivative, which is actually some very small approximation, like over some delta. Don't worry about this. Don't worry about it. We just care about the last part, which is that this, so this is how you take the derivative, which is like, you kind of take a delta t to be infinitely small, and we subtract t plus delta t minus t. And it turns out that if you take this derivative, you will get this nice thing, which is this. So we want to compute T, which is the temperature, at x for every x, which is the point, the spatial point. And this function is u, which gives us the temperature. And so this is u, this function u of t x plus delta x minus 2u tx plus u tx minus delta x. So like this is like kind of to the right plus delta x. This is left spatially minus delta x, and divide the whole thing by delta x squared. And the reason that we wanted to do this is like we want to write code to compute this thing with moving time dimension. And so this gives rise to a large class of problems that people are interested in computing called stencils. Stencils are often listed in one of the, there are lists of common motifs that arise in high performance computing, like dense linear algebra is one, stencils is another one. You can compute a lot of scientific computing problems using stencils, often more complicated than 3 points. Here we have 3 points because it's like one to the right, center, and one to the left. But in scientific computing, sometimes you can get like more than 20 points, something like that. But they all follow this high-level pattern, which is that you have some spatial grid, or like 2D grid, 3D grid, whatever it is. You have some spatial grid, and you have a time dimension. And each point in the spatial grid depends on the previous time dimension and some spatial points around it. And so for 1D space, x is the spatial dimension, t is the time, and we're moving up through time. We want to compute the temperature at every x point over time. So we're moving this way. Is there a question up there? If you have one, you can feel free to share it. So in code, to write this, for simplicity, let's just choose delta. You can actually choose delta t or delta x to be anything. And if you choose them more fine-grained than 1, then it just makes the simulation more fine-grained. Like the space points are closer and the time gets closer as well. But just to make this super easy, we can choose delta t as 1 and delta x as 1. And in code, we would write it like this. So we're trying to compute this u function, and we would actually, so like logically, you can think of it as we want to compute this entire 2D grid. One dimension is time, one dimension is space. And we're moving through time. This function at t plus 1 of x is what it is at the previous time step, plus some alpha. And then it depends on, so to compute at time t plus 1, the inputs are all at time t, which is along the t dimension, and just moving a little bit along the space dimension, like x plus 1, x minus 1 is just x. Are people clear on like what we need to compute? Yes. Here we just conveniently chose delta x to be 1. Yeah, super convenient, I know. We can choose it smaller, of course, and like we can then just update the code to do it like that. And yeah, so if you choose delta, so like you can imagine that we're running the simulation for some total time, big T, and then the total number of steps is just like big T divided by delta T. Mm-hmm. And maybe we have some total space. Like in code, you have to upfront allocate this array X, or like of X points. And if you were actually computing this entire 2D array, you would also have to allocate how many columns there are. But if you know delta T and delta X, you can do that. And the only difference is if you choose these smaller, it'll just take more time because there'll be more space and time steps. So this is how the computation looks. Let's say this is t equals 0, this is t equals 1. And at t equals 1, it depends on these 3 points at t equals 0. Left, directly below, and like lower left, directly below, and lower right. And we're computing all of these points in the next time. So like to do this one, we would depend on these 3, and then so on like that. So in the beginning of time, we have this entire array x, and now at t plus 1, we want to compute this entire row. But once we have computed this entire row, we can compute the next entire row. So then we're just going to move on to the next row, all the way up, like that. And if we have some total time that we want to run the simulation for, let's just say it's up there, then we have the temperature at every point at the end time. Okay, so yes, go ahead. Yeah, question. So we're not updating the boundary points because they don't have all 3 dependencies. So we're just not going to update them, and we're kind of just ignore them for the purpose. Like they're inputs, but they never get changed. Yeah, we can initialize that. I think we can guess. We can also initialize it to 0, probably. So since we're doing caching, how does this perform with respect to caching? And of course, it depends on the algorithm that we're going to use to compute this. The most natural algorithm is just like if we actually initialize this 2D grid, we just move left to right here, then we move up 1 column, and we move up 1 row, and then we move left to right that way. Okay. Yeah, so this is called looping stencil because you would implement it with loops. And so we have these 2 dimensions, x and t. If x is larger than the cache size, then by the time you get back here, so we need these 3 points to compute this point. And if x is longer than the cache size, by the time you come back around to here, this line has been evicted from the cache. And then you need to bring them in again to compute the points that have dependencies there. However, there is some potential for reuse, because if these points were still here by the time that you came back around, then you wouldn't need to bring them in again. And then another point is, let's say that we only cared about the value of x at the most recent time step. Like, to compute at time t+1, we only need the row at time t. And if we only care about the results of the simulation at the final layer, how many rows do we need to keep around? Do we need to keep around the entire matrix? Yes. So good. We only actually need to keep around 2 rows because to compute layer t+1, we only need layer t. Yep. One for previous and one for current. And then you can do this even odd thing where like previous and current swap 0 and 1. I think it's in the homework how to do this for it to blow, but the same idea applies. Yep. So so we're doing cache-oblivious algorithms, and now we'll talk about how to do this in a cache-oblivious fashion. So this is the looping code to compute the stencil. The base kernel is just like this. We take a pointer to some memory, and this is just the current point in the memory, left, right, center, and then alpha times the whole thing. So this is just to do the actual function in the stencil. And this is the looping part. The outer loop is over t, 0, or I guess 1, up to t-1. The inner loop is over x, ignoring the boundary points. So we start at 1, and then we go up to n-2. And yeah, so this is just the kernel. And this is what I was saying, like this even odd thing. This is how you know what row you're currently in. So for the looping version, assuming that we have LRU, how many cache misses would we need to incur as a function of big N and big T? So maybe let's start with one row. The row length is N. How many cache misses does it take to read one row of length N? Yes. How many cache, or no, N over B, right? Because, yeah. Yes, yeah. Good though. So yeah, to read a row of size N, one horizontal row, it takes N over B cache misses because we have to bring in N over B blocks. Okay, and then we have to read T of those. We're just going to multiply the whole thing by T. So if N is bigger than your memory size, this is a simple case, the thing is pretty big, and by the time you come back around, it's gone. It takes N over B to read one row. We have to read T rows, and that's NT over B. Questions on this part? Can we do better than that? Well, maybe it wouldn't be that interesting if we couldn't do better than that. So I will show you how we can. And the way that we're going to do it in cache. So the high-level way that pretty much all cache-oblivious algorithms work is through recursive divide and conquer. And the reason that that is natural is because I'm not sure how you would do like a subproblem iterative version without knowledge of the cache parameters. And yeah, so that's why it's recursive. And the way that this is going to work is that we in the cache-oblivious version, the whole space gets decomposed into a trapezoid, and the trapezoid gets cut with diagonals in recursive calls. Yeah, so the two dimensions are x and t. And basically the way it's going to work is that in some recursive calls, we cut along the t dimension. In some recursive calls, we cut along the x dimension, diagonally, horizontally. And why is this diagonal rather than, like, if you remember the tableau that we did a while ago when we talked about parallelism, we just cut into rectangles. So why do we need to cut in diagonals rather than rectangles? Mm-hmm. Mm-hmm. Yes. Yeah. Mm-hmm. Yeah, exactly. Because here, these are diagonal, and then notice that all the dependent points are contained in this trapezoid. Like, this point depends on these three, this point depends on these three, but because the slope is diagonal, they're all contained in this spatial location. So there's two cases. In the beginning of time, we start with this logical 2D grid, n by t, and there's two ways that we can cut it, either horizontally or either diagonally or horizontally, depending on which dimension is longer. And so the first kind of cut that we're going to do is called space cut, which is if the horizontal dimension is longer than the vertical dimension. In the end, we want the subproblems to fit in the cache. So we kind of, in some sense, you want to cut them like as square as possible in some way. Like if it's very wide, you want to cut it horizontally. If it's very tall, you want to cut it vertically, because you want like the problems to be squarish. So if the width is at least twice the height, then we cut the trapezoid with a line of -1 this way through the center. And then we compute the one on the left first, and then we compute the one on the right. So there are a couple of questions, which is, can we swap the order of these? Do we need to compute the one on the left first? Mm-hmm. Why? Mm-hmm. Yes, good. Yeah, because there's no right depends on stuff in the left, but left does not depend on stuff in the right. So that's why we do left first. And then we just talked about why is it diagonal and not vertical? Because if you cut it vertically like this, then left would depend on stuff in the right. Because like, let's say you cut it here, then like this point would depend on this and here. And then the other way is to cut it vertically. So if this thing is tall, which means that the width is less than twice the height. Why do we care about the points outside the trapezoid? Like, yes, we do need to calculate them. And in the beginning of time, the trapezoid is the 2D grid. Yeah. Yeah, really good question. Yes. So this is just for illustration purposes. This is after we have cut up a whole bunch of times. But when we first start very high level of the recursion, the whole thing is this rectangular 2D grid that we need to compute. So that is space, which is that you cut in the diagonal. Then the other one is time. So if time is taller than space, then we cut just horizontally through the middle. Then we compute the bottom first and then the top, because the top has dependencies on stuff in the bottom, but not vice versa. So you do the bottom first and then the top. And it is easy to cut the horizontal line through the center. Good, huh? Yes. So we compute all the points in the trapezoid first, and then using using that, we can compute all the points in the parallelogram. So this is divide and conquer. And so eventually, it's kind of a similar story to the matrix multiplication. We keep cutting, either vertically or horizontally, and at some point in the analysis, the problems will fit into the cache. If you want to cut it, you can cut it, yeah, you can cut it either horizontally or you can cut it diagonally as well. Like if you cut it this way, then the dependencies would be the same. Like you could compute this part first. Assuming that you have computed this, you can compute like this half and then this half. Like that. If you cut slope -1 through the middle. Yeah. And finally, so we have two recursive cases, one horizontal, one vertical. And finally, we have a base case, which is at height equal to 1. Because at height equal to 1, we just have this entire row, and we can compute them in any order. In here, there's no dependency between them. You just compute the next row. This is the C implementation. So the base case, so the parameters T1, T0 are like the lower point and higher point in the vertical dimension. X0, the X0 are, this is the leftmost point, and this is the slope on the left. X1 and slope, sorry, rightmost point, and then slope on the rightmost point. And the distance in time is T1 minus T0. That's how long we have to go in the vertical dimension. The base case is if these are only separated by 1. We just do, this is the loop version that we just had. And then these are the recursive calls. If otherwise, if the time dimension is greater than 1, this is we cut in space. This is we cut in time. It's not necessary to exactly understand all the details of this. The high level is, like I just said, if it's too wide, you cut it horizontally. If it's too tall, you cut it vertically. So how do we analyze this? We're going to do recursion. So for cache analysis, the bottom, so we start with this n by t grid, and we want to do better. Remember, like the high level goal is that we wanted to do better than nt divided by b, because that was what we got with looping. Ideally, we would like to see factors of m also. So how are we going to argue about this work and cache misses? Well, kind of in a similar way. Like the way that all of these arguments go is like you count the number of leaves and you count the work per leaf and you multiply them. And for cache misses, often it takes a little bit of more machinery to figure out both the number of leaves and the cost per leaf. But for work, it's more straightforward. So the work, well, the work should not be changed. The work should always be n times t, because like we're computing this 2D grid. And so the way we do that is we want to count the number of leaves in this recursion. The bottom of the leaf just fits in the cache. So W, which is the horizontal length of the leaves, is theta m. Because remember, this also depends on the fact that we're counting, or we're holding only 2 rows at a time. So to compute like this entire h by w trapezoid, we are only storing w points, because we're storing 1 row at a time. So the point at which the actual memory that the subproblem takes fits in the cache is when this thing is theta m. And the number of points in there is h times w, which is theta w squared, because of the way that we did the cutting. We did the cutting, like both vertical and horizontal, so that h is theta w. And so theta hw is theta w squared, and then w squared work, because it takes theta w squared work to compute theta w squared points. For cache misses, since in this case w is at most m, the leaf incurs this many w over b cache misses. And so we're going to argue about both the work and the cache misses. There are this many leaves. There are nt over hw, which is nt over w squared, leaves. The internal nodes is also similar to leaves in this kind of binary tree, but the internal nodes are not doing many cache misses. All the work is at the leaves. So the work is the total number of points divided by the size of each subproblem times the work in each subproblem. So that's just nt. The cache misses is the total number of subproblems times the cost of each subproblem. Now this is w over b, because we just said that the leaf incurs w over b cache misses. You multiply them. This is nt over bm, because w is theta m up there. And remember with the looping version that we had nt over b. So this has an extra factor of m in the denominator. For arbitrary dimensions, the returns are diminishing. For d dimensions, this becomes polynomial and m in the denominator. I'm out of time, so I will continue next time. Thanks.